From Ohm's law, we see that current through the human body depends on the voltage applied, and also on the electrical resistance of the human body. Your body's resistance ranges from about 100 ohms if soaked with salt water to about 500,000 ohms if your skin is very dry. Touch the electrodes of a battery with dry fingers, and resistance to the flow of charge would be about 100,000 ohms. You wouldn't feel 12 volts, and 24 volts would just barely tingle. With moist skin, however, 24 volts could be quite uncomfortable. Many people are killed each year by current from common 120-volt electric circuits. Touch a faulty 120-volt light fixture while standing on the ground, and there's 120-volt pressure between you and the ground. The soles of your shoes normally provide a very large resistance, so the current probably wouldn't be enough to do serious harm. If you're standing barefoot in a wet bathtub, the resistance between you and the ground is very small. Your overall resistance is so low that the 120-volt difference may produce a dangerous current through your body. Drops of water that collect around the on-off switches of devices such as a hairdryer can conduct current to the user. Although distilled water is a good insulator, the ions in ordinary water greatly reduce the electrical resistance. There's also usually a layer of salt on your skin, which when wet lowers your skin resistance to a few hundred ohms or less. As you can imagine, handling electric devices while taking a bath is extremely dangerous. You've probably seen birds sitting on high voltage wires and wondered why they aren't shocked. When the bird perches on one wire, every part of that bird's body is at the same high voltage as the wire, and it feels no shock. For the bird to receive a shock, there must be a difference in voltage between one part of its body and another part. Most of the current will pass along the path of least resistance connecting these 2 points, which is the wire. Very little current would pass through the bird. Suppose you fall from a bridge and manage to grab onto a high voltage power line, halting your fall. If you touch nothing else of different voltage, you'll receive no shock, even if the wire is thousands of volts above ground voltage. No charge will flow from one hand to the other because there's no appreciable difference in voltage between your hands. If you were to reach over and grab a second wire, the voltage difference would be thousands of volts and you'd be in big trouble. Mild shocks occur when the surfaces of appliances are at different voltage from other nearby devices. If you touch surfaces of different voltages, you become a pathway for current. To prevent this, electrical appliances are connected to a ground wire through the round third prong of a 3-wire electric plug. All ground wires in all plugs are connected together through the wiring system of the house. The 2 flat prongs are for the current-carrying double wire. If the live wire accidentally comes in contact with the metal surface of an appliance, the current will be directed to ground rather than shocking you if you handle it. When we say DC, we mean direct current, which means a flow of charge that always flows in one direction. A battery produces direct current in a circuit because the terminals of the battery always have the same sign of charge. Electrons always move through the circuit from the negative terminal toward the positive terminal. Alternating current, AC, as the name implies, is electric current that repeatedly reverses direction. Electrons in the circuit move first in one direction and then in the opposite direction. This is accomplished by alternating the polarity of voltage at the generator or other voltage source. Voltage of AC supplied by power companies in North America is normally 120 volts at a frequency of 60 Hz. The popularity of AC arises from the fact that electrical energy in the form of AC can be transmitted great distances without losing too much energy in the form of heat. That's it for this time. Happy physics!